This video looks at various applications of the Lorentz transformation from length contraction and time dilation right through to its role in transforming velocity components between frames of reference that are moving relative to each other. So the theory of special relativity is concerned with the motion of objects that are in inertial frames of reference. An inertial frame of reference is a non-accelerating frame of reference, that is, one in which Newton's first law of motion holds. That means a free particle is at rest or moves with a constant velocity. So an observer with an accelerometer carried with him or her would not be able to detect any acceleration whatsoever if they were moving in such a frame. So constant speed, constant velocity. Special relativity is based on two postulates. The first one is that the laws of physics are the same in all inertial frames of reference. And number two, the speed of light is the same for all observers regardless of the relative motion of the observers and the source. So let's have a look at a reference frame here. We'll call it S. And an observer here, a little purple person, sees an event and gives this event a flash of a light bulb or a firecracker going off, gives this event the coordinates t, ct, x, y and z in their frame. The use of c here is just to scale the t coordinates. It's handy for a lot of things which will show up later on. Another observer in a different frame, S prime, moving relative to the first, sees the same event, that's the flashlight going off or the firecracker going off, and ascribes to that event the coordinates ct dash, x dash, y dash, z dash. Now, this frame is moving with constant speed relative to the first one, or vice versa. The first frame is moving with constant velocity relative to this one. Alright, now let's say the two frames, S and S dash, or S prime, are moving relative to each other in a common direction along the x dash axis with a velocity v, as shown below here. And this is called the standard configuration. So when talking about standard configuration, you can think of two frames of reference moving with constant speed relative to each other. Now, let's also assume that the frames coincide at some time t equals t dash equals 0. That means we don't have any constants involved in the transformation. So, just for an instant in time, the two frames coincide at t equals t dash equals 0, and there's no loss of generality in doing that. So here's this frame moving relative to that one, or vice versa, this one moving in the negative direction relative to this. Right, both observers see the same event but ascribe different coordinates to it. So the first one in S ascribes ct, x, y, z, and the second one ct dash, x dash, y dash, z dash. How are these coordinates related? Well, due to the two postulates of special relativity, both observers will always agree that the space-time interval for their own reference frame is the same as for the other observer's frame of reference. So for the observer in frame S, this interval here will be equal to this expression here as seen by the observer in S prime. So these two space-time intervals are always equal. Any two observers in two inertial frames moving relative to each other will always agree on this statement here. That comes from the postulates of special relativity. Now, this can be accomplished with the Lorentz transformation. I'm not going to go into the algebra here to achieve this, but the end result is the following transformations for two frames in standard configuration. So t prime will be gamma, this is the Lorentz factor, times t minus vx on c. V is the velocity of the relative motion of the two frames. X prime will be gamma times x minus vt. Y dash, y prime equals y, z prime equals z. Now for these two coordinates, both y prime equals y and z prime equals z are the same because the motion is in the x direction only. So all other directions perpendicular to the direction of motion are not affected by any Lorentz contraction. So y prime equals y, z prime equals z. The Lorentz factor is given by this object here, 1 over the square root of 1 minus v squared on c squared. That can be more compactly written as 1 over the square root of 1 minus beta squared, where beta is v over c. Now we can express the relationship between the two sets of coordinates in matrix form, and this matrix here is the Lorentz transformation. This transforms from the S frame coordinates into the S prime frame coordinates. So minus beta times gamma. So this is a transformation going from the unprimed S to the primed S. The inverse transformation is achieved by replacing V with minus V and swapping the prime and unprimed labels. So this is swapped around. Remember that was minus beta on the previous page here. That's been swapped. That's now become plus. Alright, for a transformation, or boost as it's called, in the Y or Z directions, we have for the Y direction here, and for the Z direction here. So that's the standard configuration for a boost in the Y or Z directions. Standard configuration in motion along the Y-axis only, or motion along the common Z-axis only. Alright, length contraction. A rod of fixed length, A rod of fixed length is at rest with respect to the observer in frame S'. So here's the rod S', fixed length. That's its rest length or proper length in the frame S'. So this rod is not moving with respect to this frame here. Right? The rod of length delta x' as measured by the observer in S' will have a different length in S because it is Lorentz contracted in the S frame. From our transformation equation, x' is gamma times x minus vt. This describes a single event at a single point, x', xt. We can also transform with the Lorentz transformation an interval. So delta x' could represent a length, such as the length of a rod, and that will be gamma, the Lorentz factor, times delta x, its measurement in the S frame, minus v times delta t, the length of time recorded in the S frame. So the observer in S measures the ends of the rod at the same time, so that he/she has delta t equals 0. So the rod is at rest in the S prime frame. It moves past the observer in the S frame, and perhaps at either end of the rod there can be a laser beam, a laser that fires from both ends of the beam and leaves a mark on the ground in the S frame, and then the observer in the S frame in their own time can go up and at a single point in time measure the length between the two intervals. And when that's done, what is found, delta t here goes to 0, and we're left with delta x' equals gamma times delta x. So delta x' is the length in the S prime frame, and delta x is the length of the rod in the S frame. As you can see, there's a factor of gamma here. Now the observer in S measures delta x equals delta x' on gamma, where 1 on gamma is less than 1, we'll see why in a minute, and that tells us that the length of the rod in the S frame is less than the length measured by the observer in the S prime frame. So the rod in the S frame is seen to be shorter by the observer there than its actual length as measured by the observer in S prime, who is at rest relative to the rod. Now 1 on gamma is the square root of 1 minus v squared on c squared. That's less than 1 since v on c is less than 1. The relative motion of the frames will always be less than the speed of light. Nothing can travel at the speed of light except light, of course. So v is always less than c. So v over c is less than 1. If we let the length of the rod be L0 as measured in its rest frame, that's by the observer in S prime who is not moving relative to the rod, then in the S frame we call this length L. We then have the familiar relation L is L0 on gamma, where 1 on gamma is less than 1. So the observer in the S frame, who is moving relative to the rod, sees the rod Lorentz contracted and sees a shorter length than is the length of the rod in its rest frame. Alright, time dilation. A clock at rest in S prime measures a time interval delta t prime. Since it is at rest, we must have delta x dash is 0. So let's transform from s dash to s. That means we need the inverse transformation in order to determine delta t. So the inverse transformation is t equals gamma times t prime plus, notice a plus not a minus, v x dash on c squared. Expressed in using intervals now, delta t is gamma times delta t dash plus v times delta x dash on c squared. Substituting in what we know, we have delta t is gamma times delta t dash. Remember that delta x disappeared because the measurement's made in one location. So delta x prime disappeared. So we have this object here, delta t equals gamma times delta t dash. Now we let the time interval measured with the clock carried by the observer in s dash be called the proper time, and we could call that capital T subscript 0 or tau. The time interval measured in s can then be labelled capital T or small t, lowercase t. So we arrive at capital T is gamma times capital T subscript 0, where gamma is greater than 1, or lowercase t equals gamma times t. Now this gamma factor is greater than 1, so the observer in s, who measures t, records a longer time interval than does the observer who is at rest with respect to the clock and measures tau. So to an observer in a frame, in the frame S, time appears to be running more slowly in the S prime frame by this factor of gamma. So 1 second here in the rest frame of the clock, tau, may be a couple of seconds over here to S. Alright, 4 vectors. We can express the coordinates of an event as a 4 vector. So x superscript mu is x0, x1, x2, x3, and that's the Cartesian coordinates here. The Lorentz transformation for a boost in the x direction from frame S to S prime can be given by this object here, which is capital Greek lambda, with superscript mu prime and subscript mu, or in the compact form of writing the matrix like this, dx mu prime dx mu is the Lorentz transformation here. Now this is a mixed tensor of rank 2 because it has 2 indices, mixed because it has a contravariant index, the upper one, and a covariant index, the lower one. The inverse transformation is given by, see how these are flipped? The matrix itself is flipped from the previous one, the prime's now down below, and notice here the minuses are gone. So for example, t, time measured in the S frame, is gamma times tau, time measured in the S prime frame, in the rest frame. So lambda 0 subscript of 0 prime to t, that would be written as dt x0 dx 0 prime, which is dt d tau. Look here, dt d tau is equal to gamma, and that's exactly what we have up here. The 0, 0 entry, this top left-hand corner entry is gamma. So that's how you generate these terms from the coordinates themselves. Right, now the world line of a particle in frame S can be parameterized in terms of the proper time tau of the particle as measured by a clock that it carries with itself. So imagine this particle flying along through space, it carries its own clock, it measures time tau, the rest time. X superscript mu is x mu of tau, so we're parameterizing it in terms of tau, so we get c t of tau, x of tau, y of tau, z of tau. Now the forward velocity of a particle is the tangent vector u to its own world line, and we'll pick that up in a future video. The following relationship between coordinate and proper time is coordinate time t is gamma times tau, proper time. Differential form of that is dt is gamma times d tau, and we can rearrange that to have d d tau is gamma times d dt. Now the velocity components of the particle as seen by the observer in the S frame are given by u superscript mu is dx mu d tau is gamma u dx mu dt. Now, it's equal to these components here. So here's the 0, 0 component, the gamma u c, and then gamma subscript u dx1 dt. And these are the components for velocity vector of a particle as seen in the S frame, but in a general direction. Now what that means is, here's an S frame here, here's an observer, and here's an object moving relative to the observer. So here's the S frame observer. If you can imagine, these axes might be, if you can picture them like steel bars, and the observer is glued to the bar there and can't move, but this object is moving relative to the observer, and hence the gamma subscript u, because it's moving with speed u, in the general direction or whatever, but the speed is u. In this particular case, it's moving along the x1 axis here, as in standard configuration, but it could be moving in any direction. So this is speed u, hence the gamma subscript u, because remember, gamma depends on the speed, because remember, gamma is 1 on the square root of 1 minus u squared on c squared, if you remember from previous slides. So the speed u, hence gamma subscript u. So that's what that observer sees. A second observer standing perhaps next to the first and viewing the motion of the object will record the same components. U superscript mu prime, the prime indicating a second separate observer. Now there may be relative motion between the observers, they may be standing next to each other, they may be a distance from each other, but there's a second observer and they're recording movement. So they'll have dx mu prime d tau is gamma mu prime, u prime, gamma subscript u prime. Now u prime is the relative speed they see the object moving at relative to them. So they see the same object, but moving at a speed of u prime. So they have gamma subscript u prime there, dx mu prime dt, and here's their components. The prime here above each of the u's indicating that it's a second separate observer from the first. But if the second observer is moving to the right of the first at speed v in standard configuration, then we must use the Lorentz transformation to determine what they see. So the Lorentz transformation from S to S prime is given by this compact object here. In matrix form, this is, okay, here's the observer in S, here's the observer in S prime, and then observer in S prime is moving with velocity v relative to the observer in S. Hence the transformation is subscript v, because the two frames are moving relative to each other with speed v. Within S, the observer sees the object moving with respect to him or her with speed u. Within S prime, the observer sees the object moving with respect to him or her with u prime. Okay? But the two frames are moving relative to each other with speed v. Now, if we multiply this out, then in the first line, we're going to have gamma u prime c is this object here. When we do the matrix multiplication, just the first row. If we then factor out gamma subscript u, we get this object here. All right. And then if we take the reciprocal, we end up with this. A little bit of algebra there. And that'll be handy on the next page, so just keep that in your mind somehow. Alright, now looking at the second row, we get this object here. And if we multiply by the reciprocal of this object here, we get u superscript 1 prime by itself. And we'll have all this over here. Remember this bit from the previous page. When we do the algebra, gamma subscript v cancel out there, but when we do the algebra, we end up with this transformation equation here, relating the velocity components between frame S, which is u1, and frame S prime, which is u1 prime, moving relative to each other at speed v. Alright, so an example, an observer on Earth, frame S, sees a spaceship, frame S prime, moving towards them at 40% of the speed of light, whereupon they launch a probe towards the spaceship at a speed of 0.3, or 30% of the speed of light. And what speed does the observer on the spaceship see the probe to be approaching at? Well, here, the observer on Earth, in frame S, sees the spaceship coming towards them. It's in the negative x direction, not moving away from them. So the speed they record of the spaceship coming towards them is negative 0.4 c because it's in the negative direction. The observer on Earth sends out a probe at 30% speed of light in the positive x direction, so hence plus 0.3 c. But what does the observer on the ship in the primed frame S prime see? Well, the observer in the S primed frame sees this, sees all of this. That's the 0.3 minus negative 0.4 over this object here. When we do that, we get 0.7c over 1.12. We get 63% of the speed of light. So the observer on the ship sees the probe approaching him or her at 63% of the speed of light. Now, if you remember in the standard configuration, we have S prime moving to the right, to the positive x direction, moving away from S. Here, the spaceship is moving towards S, hence the minus. When we do all this calculation here, the observer on the ship sees the probe approaching at 63% of the speed of light. And that's that.